Hello everybody, welcome back to Calc 3. Plan for today is I have a quiz for you on Standard 3, and then we are going to jump into Standard 4 and talk about how you can find equations for and go about graphing lines and planes in 3 or more dimensions. I've got my usual office hours, huzzah, this week. So today and Wednesday, the hour before class, and from 2 to 3. Tomorrow, from 10 to 11, and from 1 to 2. As far as homework problems go, I have posted some practice problems from Standard 4. Some of them, particularly the ones in 1.2, you should be prepared to tackle today. The ones involving planes we won't get to until Wednesday. As way of apology for missing class on Friday, I have 2 jokes of the day. First one. How are mathematicians like the Air Force? Mathematicians are like the Air Force, in that they both use pilots. And second of all, here's a Calc 2 joke. Suppose you start with 1 rabbit, and then you add to that half a rabbit. And then you add to that a quarter of a rabbit, and then an eighth of a rabbit, then a 16th of a rabbit, and so on. What do you end up with? Well, if you sum up the series, 1 plus a half plus a fourth, etc., you should end up with 2 rabbits. But practically speaking, you can't really actually do that unless you're willing to split hairs. All right, got a quiz for y'all for today. Can you go ahead and pass out? Go ahead and take about 10 minutes or so on the quiz. As per usual, I'll let you know when you have about 45 seconds left. And, yeah, have fun. Also, I have quizzes to pass back to you, which I'll do after you take this one. I think that might not be enough. Go there. Sorry for all the clicking. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes forward, please. I also have some stuff to pass back to you from this past week. So, Katie. Tim. Avery. Lindsay. Sarah. Hannah. Hiya. John. Gary. Luke. Dog. Wait. John. Oh. Avery again. Sorry. Emily. That's McCoy. Renu. Olivia. Will. Laurie. Jacob. Jack Smith. Jackson. Holly. Anna. And Matt. Okay, so a couple general comments on quizzes and grading. I've started posting quiz solutions on Blackboard. Keep in mind, I'm only going to be posting solutions for the quiz A's, so basically the quizzes that you take in class. I generally don't post solutions for retests online. The main reason being, if you took, just because you maybe retested on Standard 1 version 1B last week, Perhaps someone else is going to retest over in a month or 2 months from now. Not everybody's testing at the same time, so I'm just not going to post solutions to those. But for the version A's, everybody takes that the same day, so those will get solutions on Blackboard. And I'm happy to talk about solutions to any quiz once you take it. Let's see, some quiz solutions. I've also been, like I said, posting solutions to these worksheet packets. Encourage you to check those out. I was going to open up Blackboard to show you a few things, but Blackboard appears to not be working today, which is a tragedy. And very typical for Blackboard. Any questions or comments before we start adding on the new stuff for today? All right, let's do some math. So, first three standards were all kind of related to properties of vectors. Namely, what are vectors? How can we add them? Do scalar multiples? Do dot products? Do cross products? What do these things all represent geometrically? How do we compute them? And kind of been focusing on properties of vectors so far. What we're going to be doing today is to take our first look at how do we graph functions in the 3 space or higher. And in general, how do we find formulas for lines in 3 and higher dimensions? So, start off with, I'd like to do a quick little review of how we define lines in R2, meaning in previous math courses. If we're writing y as a function of x, can anybody tell me the slope-intercept formula for a line?
Y equals mx plus b.
Indeed, right? Y equals mx plus b. I'm going to write it as y equals ax plus b, just because we're going to use a to refer to slope for the multivariable lines that we do. But in general, this is going to give you a line in R2, where the value a is going to refer to the slope of that line, and b is going to be the y-intercept. But in particular, b is going to be a value that helps us find a specific point on the line. And so if I were to give you something like y equals 2x plus 6, for instance, you would know that 0, 6 is going to be a point on the line, and that the slope of 2, meaning delta y over delta x, sort of as x changes, how much y changes by, it's going to be by a factor of 2, meaning if we go 1 unit in the positive x direction, that'll lead us 2 units in the positive y direction. So that our lines in R2 are going to look something like that, where we just have 2 scalar values that kind of determine the line. This a value is going to give us the slope, which tells us kind of which direction the line is pointing. And b, our y-intercept, just helps us find a specific point on the line. Because there's infinitely many lines with a slope of 2, but only one of them is going to pass through that point, 0, 6. Hence, that's how we kind of typically talk about lines in R2. And yes, you could put them in standard form, you can put them in point slope form, you can, I'm sure in previous math classes you've done oodles of stuff with that equation. But slope-intercept kind of is going to be the one that we build off of. In higher dimensions, you can actually define lines in a similar way. So let's say, generalizing this, you can actually generalize this formula for a line to say R2 and up by using the exact same sort of setup, a very similar looking formula. R of t is equal to at plus b, where this time, instead of treating y as a function of x, we're going to define our line to be a function of a new variable t, which oftentimes we'll call the time parameter. Where now, just in the same way that we did before, we're going to have this A value, where A is going to tell us the slope of our line, and B is going to give us a way to find a specific point on the line. Sorry, it's probably being blocked a little bit by the overhead. Except looking at these two different formulas, can anybody tell me a way in which the A and the B and kind of the R2 slope-intercept formula for a line are going to differ from the A and the B in this generalized formula? What do you know? Just from only from looking at the two equations, what's going to be different about our A and B? Exactly. A and B, and what we're going to be doing, are not going to be scalar values, not like single numbers like 2 and 6. Instead, our A is going to refer to a slope vector. And this value B at the end is not going to be just a single number referring to the y-intercept anymore. B is going to be a multi-dimensional vector that's going to tell us how we define our lines. So, before we dive too deep into looking at lines, though, I want to talk a little bit do a little bit of review of something I'm guessing most you likely saw in Calc 2, which is defining things in terms of parametric coordinates. Pull this up for a second. So, parametric coordinates is going to give us a way to look at functions. Parametric, you might have seen it written equations or coordinates. They kind of refer to the same thing. Typically, in R2, STD being standard functions, you always see them written as y is a function of x. Meaning y, meaning you're going to look at points in R2 in an xy plane where what your x coordinate is going to tell you what your y coordinate is. So that y is always going to depend on x. In parametric coordinates, x and y are independent of each other. And depending on your dimensions, you could say and z, w, etc. are all dependent only on a new variable t. And so in parametric coordinates, what you'll often see is something like this. X of t is 5 cosine t. Y of t is 5 times sine of t. And say z of t is, 1/2 t. And the key difference between looking at a function just written in standard form, y equals a function of x, and parametric equations, taking all of your variables like x, y, and z as being a function of a variable t where t doesn't actually correspond to any coordinates. There is no t-axis in R3, for instance, or in R2. But instead, let's do an example in R2 as well, just so you have something. Instead, when you're dealing with parametric equations, x, y, and z are all determined by plugging in some number for t and seeing what results when you look at the corresponding x, y, and possibly z values. So, just as a little bit of a demonstration, I've gone ahead and plotted on CalcPlot 3D these three equations. And I'd like to just take a quick look at what is the graph going to look like that these equations produce. Let me pull down the screen for a second. By the way, this software, CalPlot 3D, I've been, oh my gosh, blue in my eye. This software I've been using, CalPlot 3D, I've posted a link on the Blackboard page to this website. So if you want to go outside of class, you can actually go and try graphing these things for yourself. So I went ahead and made an XYZ plane, and I've told it, it's not showing right now because I haven't told it to yet, but I've told this website to plot the parametric equations given by x of t is 5 cosine t, y of t is 5 sine of t, and z of t is 0.5 times t. Let's see what happens when we tell this website to actually plot these coordinates. We get a slinky, or a coil, take your pick, where this blue graph is going to be the set of all points that can be expressed in this way. And so if I wanted to plug in a specific, take this out. If I wanted to look at some specific points on this graph, I could do that by saying at t equals, say, 0, equals 0, it's telling me I'm getting a point right here. And as I change my t value, I get different points on this sort of coil-like shape. If I let t go down to -20, it takes me down there. T equals, I don't know, 7.6 is giving me a point right here. And in general, for different values of t, you're going to get a different point on this slinky-like shape. So, as just a quick little example, let's say I wanted to find out at t equals 0, it's giving me a point that looks like right here. How could I actually go about and find the exact coordinates of that point?
Plug in 0 for all t values in each of the 3 equations, and then you have a point with all 3 coordinates.
Yeah. If I want to find out what is this point at t equals 0 for these 3 equations, I just have to plug in t equals 0 into each one and to see what gets spat out. So, for example, we could say that at t equals 0, we'll get that x of 0 is 5 times cosine of 0. Cosine of 0 is 1, so that's just going to give me 5. Y of 0 is going to give me 5 times sine of 0. Well, sine of 0 is just 0, so this gives me 0. Z of 0 is going to be 0.5 times 0, which is just 0. We can say that at t equals 0, we're going to get the point 5, 0, 0. And so all of these points that we get from just looking at different values of t, at t equals 0 versus t equals 5.2-ish, are just what's going to result. There's a way to make this point bigger. I don't think there is. It's just a result of plugging in different values of t into the function. And so this slinky-like shape that we're going to get is just going to be the set of all of the different points that you could get by plugging in different values for t. This is kind of how parametric coordinates work in general. It's just, there is no t-axis. X, y, and z are not dependent on each other, but only dependent on this t variable. And to find a point on your graph, you just have to plug in individual values for t into all of your equations. 5 cosine t, 5 sine t, 0.5 t. And then depending on what your equations tell you, that's going to give you different points on the graph. And when you just combine all those points, this is the sort of shape that you might end up with. Does anybody have any sort of questions or comments about parametric equations like this and how they work? In general, we're going to be using parametric equations in a few different ways throughout the semester. The way I like them the most, though, is that they're really helpful in helping us to define lines and planes, which is kind of going to be the focus of standard 4. So that aside for a moment, let's go back to our equation for a line for a second and see if we can kind of make sense of how we would actually go about drawing these sorts of lines. And the way it's going to work out is going to be something like this, where in R3, for instance, we can say that the line that's going to pass, through the point P0, which is given by coordinates B1, B2, and B3, and that is parallel to the vector A, which I have written out in my notes as A1I plus A2J plus A3 times K, because that's how the book writes it out. But if you want, you can just write it out as A1, comma, A2, comma, A3. So, just to give you a sense of what we're talking about, we're saying, let's say you have some point P0 in space, and you have some vector A, doesn't have to go through P0. If we want to find a formula, in other words, for the line that happens to pass through the point P0 and that's going to be parallel to the vector A, parallel meaning they point in the same direction, so this line here that passes through P0 and that goes in the same direction as A is going to be this equation that we found on this board here. R of t is going to be vector A times t plus the vector B. Or if you prefer, you could write it out as A1, comma, A2, comma, A3 times t plus the vector B1, B2, B3. In parametric equations, you would get that your x of t, y of t, z of t, we can all find formulas for. Writing this whole out as one equation, we could actually write in terms of just a single set of 3 coordinates. If we were to combine these two, do this scalar multiple, multiply by t, and then add these 2 vectors together, we would get a single vector with 3 components to it. What would be the first coordinate of the expression we would get if we combined all of this into a single vector? Jackson? It's going to be A1t plus, what did you say?
Plus B1.
I say it needs to be plus B1, just the first coordinate of what you would get when you combine these. Because if we multiply and then add these together, these will combine to give us A1 times t, A2 times t, A3 times t. And then when we add B1, B2, B3, we'll get A1t plus B1, A2t plus B2, and A3t plus B3. Which, if we separate that out into x, y, and z components, we're going to get that x of t is A1t plus B1, y of t is going to be A2t plus B2, and z of t is going to be A3t plus B3. And this is going to give us our parametric equations for how we can define a line in R3. Just where x, y, and z each are going to look like linear formulas in and of themselves, y equals a2t plus b2 sort of looks like y equals mx plus b, or ax plus b. And each one is just telling us how if we wanted to look at points on this line, what we would have to plug in for t to get a point on this line. So if we were to plug in t equals 2, that would tell us the x, y, and z coordinates of a point on the line, this line L that I drew right here, that passes through P0, and that's going to be parallel to this vector A. So this is a bit messy to kind of talk about in general. Lots of kind of variables that I think are floating around. So let's do an example where we actually try and find an exact formula for some line that does some things that we want. And I'm going to be on the second page now of this packet. Let's say we were interested in finding an equation for the line that's going to be passing through -4, 5, -1, and that is parallel to the vector 3, 2, -1. So I'm going to pull this down for just a second. Okay, wake up. Let's say now we're looking in 3 space. We have this point right here at 4, 5, -4, 5, -1. And a vector 3, -2, 1. And what I would like to do is to find the line that passes through this blue point I drew, -4, 5, -1. I had a way to take this off the screen so you don't see the answer. And that also happens to point in the same direction as this vector here. Meaning, in other words, I want to find the formula for this line, which this vector kind of gives us tells us where the line's pointing, and so that this line happens to pass through this big blue point here at -4, 5, -1. So I turn this off for just a second. So what do you all think we should do? Well, when you're going to need a vector, I think it's when you're finding a formula for a line, it's always good to start off with the general equation like this: R of t equals at plus b. The question is going to be, though, which vector is going to be our b, and which vector is going to be our a in this scenario. So what do you all think? Anybody give me a proposed vector b that we could say sort of is how we find a point on our line? Yeah.
We know that it's passing through the point, -4, 5, -1, so we can use that as our b vector.
I like it. Yeah. Our b vector is just going to correspond to some point on the line. Doesn't matter which one. We're given this as a point on our line, so that's a great candidate, I think, to be our b vector. How about an a vector? In other words, a vector that's going to correspond to the slope of our line. Meaning a vector that tells us which direction our line is going to be pointing. Okay?
The vector 3, 2, -1.
Yeah, this will be our vector A. When we say that we want our line to be parallel to this vector, 3, 2, -1, what we really mean is we want it to be pointing the same direction as 3, 2, -1. That's what we meant in general for things to be parallel, is they point in the same direction. And so, if we just plug these in for A and B, we'll get that our A is 3, 2, negative 1, and our B times T, and our B is negative 4, 5, negative 1, which we can combine into a single vector if we want. 3t minus 4, 2t plus 5, negative 1 times t, so negative t minus 1. And if we were to write that out in parametric coordinates, we would just have to peel off the first, second, and third coordinates of this expression respectively. So our x of t will be 3t minus 4, y of t is 2t plus 5, z of t is negative t minus 1. And in fact, shoot. Does everyone have that XYZ written down? I'd like to pull down the projector and bring it a little too close to it. Which in fact, if we look at our line, is exactly what I had. I mean, I wrote it as negative 4 plus 3t instead of 3t minus 4, but it's the same thing. 3t minus 4, 2t plus 5, negative t minus 1 happens to give us this line that is parallel to our slope vector. It's parallel to the vector 3, 2, negative 1 here. And it also passes through this point, negative 4, 5, negative 1 that we were given. If you go into CalcPlot 3D, you can tell it to graph individual points, which just make them appear as dots. You can tell it to graph vectors, and even change it to be displacement instead of position vectors. You could tell it to graph a space curve, which is something with parametric coordinates. And there's some other features, which is going to be stuff we'll talk about later in the semester. If I were, for instance, to take, one thing I'd like you to note is that if we were to take this slope vector, 3, 2, negative 1, if we were to translate that to be a displacement vector that happened to start at negative 4, 5, negative 1, before I hit enter and actually translate that vector, what do you think would be the relationship between this vector, our slope vector, and the line, if we were to just translate the vector over so that it started at this p naught here rather than at the origin? In other words, what would it look like to move this so that it's positioned, so that it starts at that point?
It'll be orthogonal to the line.
It'll be orthogonal, so perpendicular to the line?
Yeah.
Let's see.
Oh.
Does that look orthogonal?
No.
Unfortunately, I don't think it quite works. It's not orthogonal. In fact, we actually explicitly said we want our line in this slope vector to be parallel to each other. So they're actually going to be pointing in the same direction as each other. So, follow-up question. Let's move this back to the origin for a second. What would be different if I chose a different slope vector? Let's say instead of 3, 2, negative 1, let's say I chose negative 6, negative 2, negative 4, excuse me, negative 2. Nope, that's not it either. Multiply by negative 2, negative 2. Oh, this should be positive 2. That's right. So let's say we chose a different slope vector, where the slope vector we chose was negative 2 times the original slope vector. So if this was our original slope vector, this new slope vector, it's going to be the same vector, but pointing the opposite way and twice as long. How do you think the line, what do you think would be different if we were to choose the same point and this new slope vector? How would that change the line that we would get if we wanted to have a line that passes through this point and that is parallel to this new vector? Holly, any thoughts?
It wouldn't change it
Why not?
because the new vector is parallel to the first one, so it would still have the same
Ah, so this new slope vector is anti-parallel to the original, meaning it and the original point in exact opposite directions. I don't know why I felt like doing that. And so, if we were to take a line that is parallel to this new red vector and it passes through the same point, I agree, we would get the exact same line. So let's see what that new line would look like. I'm just going to erase this. So some space. So if we did that, we would get our R of t. So this would be the new line formed with slope vector -6, -4, 2, which is -2 times our original slope vector. So our original slope vector, 3, 2, -1. What we would actually get is that our R of t would now be -6, -4, 2t plus our vector b, -4, -4, 5, -1. Which, when all is said and done, would lead us to these parametric equations. X of t is -6t minus 4. Y of t is equal to -4t plus 5. And z of t is 2t minus 1. And I have a question for you. Do these three equations look the same as these three equations? I don't know why I decided to pick on you, by the way. I was just... Yeah, these look a little different. They have the same constant terms, -4, 5, -1 at the end, but the slopes of all the lines here are double the slopes of all the lines here. So here's my challenge question for you, one I want you to spend a couple minutes thinking about before we come back to an conclusion as a class, and I encourage you to talk to the people next to you. Why does this set of equations produce the same line as this set of equations, even though these equations are clearly not the same ones as these? So go ahead, take a minute, and if you can, and I encourage you to talk to your neighbor and see if you can determine why these two lines come out to be the same, despite the fact that they're not exactly the same three equations.
What do you think?
You're not solving this equation, you're solving But at the same T, it'd be a different spot. It'd be a different spot on the line, but in the same T, right? It's still have the same relationship. Then it's all out.
I didn't divide by 2 at the end, but that's like
Well, the actually, y is aren't different, like y is not.
That's the only thing I can think of is that it depends on each comes back to the bit of
The x of p is, well, it's not arbitrary, but it's, if you compare that x of p to that y of p, it's different, but not comparing different y of p offsets. As long as the ratio is like
That's true. Each of the slopes has
So let's come back together for a second and try to talk about this. Why do these two sets of equations, in which the equations are not the exact same, still somehow produce the same line? Heard some good thoughts as I was kind of trying to listen to various groups around the room. Sarah, what are your thoughts?
Because what might be called the slope of these lines, the vectors are scalar multiples.
Yeah, these are certainly scalar multiples of each other. So, why does that matter? Or what effect does that have on things?
Because one of them is almost like reducible to the other in the sense that, like if we take an mx plus b equation, that 1/2 x plus b is the same line as 2/4 x plus b.
Wow, we literally stole the exact same example. I don't know if I said plus 3, but 1/2 and 2/4 that I had in mind. Yeah, I totally agree with what you're saying, Sarah. It comes down to the fact that it doesn't matter the exact magnitude of your slope vector. It only matters in which direction it points. And if they point in the exact opposite directions, that's also totally okay. And the fact that, and by the way, the fact that it's okay for the slopes to point in exact opposite directions and still give you the same line is going to come down to the fact that lines go on forever in both directions. So to be parallel to this A on the left is going to be the same as being parallel to this A because the line goes off forever in the same direction as this vector and in the exact opposite direction of the same vector. Goes on forever in two directions. And so I really like your analogy to how it comes out to the fact that in Calc 1, when you're looking at slope, where your slopes are just scalar values, y equals something like 1/2 x plus 6 is the same as y equals -3, -6 x plus 6. Because the slopes turn out to be the same even if they look different. One's just telling you, oh, if you move 1 unit in the positive x and 2 units that rise over 1. So delta y over delta x. If you move 2 units in the x, that's going to move you 1 unit straight up. Or if you go negative 6 units in the x direction, that's going to take you 3 units straight down. Either way of looking at a line is going to come out to the exact same thing. It's going to produce the same line in the end if your sort of ratios of rise over run are the same. Whereas in our multivariable example, if our ratios of our slopes vectors are equal, meaning if one is a scalar multiple of the other, if the how you change 3 to get to negative 6 is the same as how you change 2 to negative 4 and negative 1 to positive 2, then the lines that you're going to get from looking at those slope vectors come out to the exact same line. Whereas if they're not scalar multiples of each other, if we change 3 to negative 1 to be something like 3 to 100, that would be a slope vector that points in a different, not opposite, but not same direction, and thus would produce a line, and that would produce a different line. Because the line would pass through the same point, but would be pointing in a different direction. If our slope vector were something like this, we would get a line that looked like this instead. It's a very subtle reason, but it ultimately boils down to the fact that 2 lines can, in parametric equations, might have different equations and yet still geometrically describe the same set of points, as long as one of their slope vectors is a scalar multiple of the other. And I should clarify, a non-zero scalar multiple. If our slope, if we just said, oh, multiply by the scalar 0, that would be saying, all right, here's my slope vector. Not very helpful in terms of telling you which direction your line should be pointing. What questions or comments do you have about that? Alright, you're all free to go for today. When we come back on Wednesday, we'll do the other example with lines, find a line that goes between 2 points, and then we will also start talking about how to define planes in 3 and higher dimensions. Because the planes is going to turn out to be related to properties of the cross product. Have a good one. So that would be saying, like if you were to look at, say, erase this one, y equals 2x plus 1 as opposed to y equals 4x plus 1. This one, the slope would look like 2 over 1. This one would look like 4 over 1, in which 1 is going to tell you if you go 1 unit in the x, you go 2 units straight up. One's going to tell you if you go 1 unit in the x and then you go 4 units straight up. So the key difference here is the fact that the ratios of change in y over change in x to each other are not the same value here. So here, delta y over delta x. If the change in y over change in x is 2 over 1, if we multiply both the top and the bottom by the same thing and took like 3x over 1.5, for instance, then I claim this produces the same number for the slope because the change in x and the change in y are changing at the exact same rate, going from here to here. Just like how if we were to multiply our slope vector, which you could sort of think as being a change in x, change in y, change in z vector, multiply everything by -2, we end up getting something that produces the same line. It's very subtle. It's a subtle difference, which is why I kind of wanted to spend some time talking about it. Sure. You can't visualize it very well. You can't visualize it in the same way as just looking at a single arrow and saying how steep does this arrow look. In like 3 dimensions and higher, you really have to think of the slope vector as just being, I'm just going to point in the direction that your line should go, rather than something that says, here is how steep it should be at any given point. The steepness is actually going to be what we're going to get to in a few standards from now. That'll be the derivative of our of each of the individual components. But the vector itself, that'll tell you this is how steep it is in the x direction. This is how steep it is in the y direction. But we won't be doing that for parametric coordinates. We'll be doing that for different types of functions. And here the slope vector is just telling you, oh, the slope vector is telling me that way. Go that way. Go that way. And not like the slope itself is not giving you this sort of ratio as a single fraction. It's just writing out each of the components individually.
Okay. Good. So it's a vector, it gives you the direction.
Exactly. Not this sort of rise over run thing,
Yes.
which it is in calc, in R2.
Okay.
No problem.
I just want to let you know Wednesday I will not be in class
Oh, no.
because of basketball. We have something scheduled, like literally during this time.
No worries.
So I'll just watch the video and
Oh my goodness gracious. Hold on.